Okay, this is chapter 11, two sample tests. And we're going to talk about independent samples, hypothesis test. In chapter 11, we're moving from where we were, single sample compared against a population, to comparing two different samples. So at the end of this chapter, you should be able to figure out which test to use. There's two varieties of tests in this chapter. You should be able to figure out which one of those two you should use, and you'll be able to do these things. All right, so there's two varieties in which we can, two experimental designs that we can have in which we would need to compare two different samples of behavior. The first is what we call independent samples. And in an independent samples design, we have two separate groups of individuals with no overlap or connection. It is two different groups of people. This is where we would use random assignment. If we have an independent variable, we would use random assignment to get two groups. Or we could be comparing two groups of occupations, say lawyers versus doctors. We could be comparing sophomores versus seniors. But what makes it independent is that there's no overlap or connection between the two. Someone can only be in one of the two groups. Often this is called a between groups test because we test the hypothesis by comparing between two different groups of individuals. For example, we might ask a question about how many hours per week people work. Do men work more hours per week compared to women? That would be independent samples because we have two groups. Someone can only be in one of the two groups. So we would get our measurement, our dependent variable for men, compare it to the dependent variable for women. Another example would be, does class type affect learning? I might get a learning episode, a class, and randomly assign students to an online version of that class or an in-person version of that class, and then afterwards assess their memory for the class. So I could do that in the lab where the class is a one-shot, non-grade kind of experience, and people come in and they do an online activity or they see an actual lecture. This could also be done by looking at existing classes. I could look at an online version of Psych 100 and compare it to an in-person version of Psych 100. In all of these situations, what we've got is independent samples. Someone is in one and only one of the groups that are being compared. We're going to talk about independent samples first, but before we go further, just as means of comparison, I want to talk about the other variety of two sample tests. And this is what we call a dependent sample test. And then with the independent samples test, we can think of two samples of people from populations where there's two different groups of people. With a dependent samples test, we've got one group of people, so there's some overlap or connection to the two samples. And it's really, to think of it as we have two samples of behavior from the same people. The most common version of this is called a repeated measures test. I get one sample of people, they perform some task, I record the data, and then that same group of individuals performs a second task, and I record the data on the second task. That would be repeated measures. Sometimes this is called within groups because it is the hypothesis is measured within a single group of individuals. Within that single group, we can get two samples of behavior. Now, the other way we could have a dependent samples test is imagine we were doing a twin study. All right, we have one twin in one group, another twin in the other group. It is two different sets of people. It looks like independent samples, but there's a connection between the two samples. So that would be appropriate to use this dependent samples test. As an example of dependent samples, we might ask a question about people's tolerance for pain and measure their tolerance for pain before or after listening to soothing music. So this would be a classic kind of before and after or pre and post study. We'd measure people's tolerance to pain before using some dependent variable. Then there would be the treatment. They listen to the soothing music. And then afterwards, we measure their tolerance for pain again. Another way to ask this question would be about learning. Do students learn more in a library or in their dorm room? So I might get a group of students and ask them to study a chapter from Intro Psych in the library, and then get that same group of people, have them study a different chapter of Intro Psych in their dorm room. In both cases, I would test them on what they studied in each condition. In both of those examples, right, it's two samples of behavior. I have a sample of behavior before and after. I have a sample of behavior studying in a dorm. I have a sample of behavior studying in the library. But it's from the same individuals. That's what makes it dependent samples. We'll talk about how to do this test later on. It's really a special situation when you do repeated measures. Both of these are going to involve t-tests, and here's a chart reminding us that t-test is really a family of curves where there's a different curve for each n or degree of freedom. And in this, you see that with the fewer degrees of freedom, if you look at the red curve for n equals 1 versus the green curve for n equals 30, the fewer degrees of freedom, they're a little shorter in the top and then wider in the tails. So that was why the critical value changes as a function of n or degree of freedom. But in both of these tests, we are going to assume that we do not know what the population standard deviation is. We're not going to know that. So that makes t-tests appropriate here. In fact, in an independent samples test as well as the dependent samples test, we're not even going to know what the population mean is. We can do this test without knowing the population mean. And we can get by that way because we can figure something out logically to take the place of our unknown mu. And since it's just involved in logic, we can push on. But without sigma, we need actual numbers for the formula to find the denominator of the t-test. So we have to estimate sigma, but with mu we can get by. So here's how it works. With independent samples, we've got two different samples of individuals. Theoretically, they could be coming from two different populations. For example, take this example of the online students. The online students come from a population of students who would take, every student who took an online class. So in my experiment, with my sample, I have sample statistics. I have a sample mean, x bar. I can figure a sample standard deviation, s. I can do all the descriptive statistics on the sample of online students. Theoretically, they represent mu and sigma. I don't know what these population values are. I have no idea what the population of online students would score on a particular exam or test. But even though I don't know the actual numbers, doesn't stop me from thinking about them theoretically. So here I have a sample of students. I know the sample statistics, but the mu and sigma are unknown, and I don't know their exact values. I know they exist, I just don't know what they are. It would be the same for the in-person students. I have the sample statistics. I can figure out everything I know about the sample. But the mu and sigma for in-person are also unknown. We can still do a t-test thanks to logic and good old Gossett, who developed the t-test. But thanks to logic, we can compare two samples without knowing what the population parameters truly are. And here's how it works. Think about the null hypothesis, We can think about a null hypothesis without knowing the values for mu through logic. Now this is where it kind of takes a leap. In the prior examples, we knew mu. We could compare whether a sample was better or worse than a population mean of 100 on an IQ test. Now, we don't know anything about the performance of these students on the tests in either population, but we can still use logic to come up with a number that we can use to tell us some things about performance. So think about this, right? Let's think about the null hypothesis. Does class type, online versus in person, affect learning? Well, the null hypothesis, as you know, is the hypothesis of no difference. So logically, right, if we assume there's no difference, then the population mean for online equals the population mean for in person. And the logic of not different tells me that I can use an equal sign. No matter what the values are, if they're equal, they're the same. That's how we can do this test, through the idea of not different. So the null hypothesis for an independent samples test is going to look like this. Let me get my cursor here so I can play with this. Let's use red today, right? There we go. Logically, right here it is, right? Null hypothesis. There's no difference between the populations from which these samples are drawn, right? Whether people are learning online or in person, it doesn't make a difference. Well, look what happens if we set it up as a subtraction. We take one population mean, subtract it from the other, and we get a 0. We get a real number, even though we don't know what the value of either of these population means truly is. Because no matter what they are, if they were equal to each other, if we subtract a number from itself, we get a 0. We get a real number. So we can do this test without knowing the values for the population means. Because if we assume that they're the same, right, the subtraction leads us to 0. The logic of these hypothesis tests in this chapter are based upon this logic of comparison, of subtraction. And if two things are not different from each other, and we subtract one from the other, we get a 0. So the null hypothesis for this test is always going to be looking like this. The unknown population relative to the first sample versus the unknown population relative to the second, right? We used to just have mu question mark unknown. Now we've got two unknowns. The null hypothesis is that they're not different from each other. The alternative hypotheses for these tests are really, they're kind of the same signs that we're used to. We could have two-tailed, we could have one-tailed. So let's consider a two-tailed option, right? Does class type affect learning? Affect is a vague word. Affect means it could be better, it could be worse. Affect just means there's a difference. One of these might be higher than the other. So if our null hypothesis is this one, that mu online equals mu in person, the alternative hypothesis would just be the difference, right? Mu online is different from mu in person. We don't know in this case which condition leads to better learning. We'll be able to tell afterwards if we reject the null hypothesis, but at this point, forming it, right, this is a two-tailed hypothesis test. We don't know which one. We don't know what exactly to expect. So when we set up the rejection region, it is going to look like this. And you can imagine as a t-test, we're going to be filling in the values, the critical values, that go along with those shaded rejection regions. Excuse me. All right, so let's consider one-tailed hypothesis test. And it gets a little bit curious with the one-tailed test. And one thing that's important to do with these tests is, because we're dealing with differences, is always keep the two groups in the same position relative to each other, right? In this one, online learning is always going to be first in the ordering, right? That matters. So let's ask, is online learning better than in person? Well, then what I'm saying is that the population mean for online will be greater than the population mean for in person. So I can line those two up using the same order that I have been using so far, right? The same order is in the null hypothesis, and that puts a greater than sign between the two, right? And that tells me that online learning is better than in-person learning. Now, the funniness of language, right, is the same thing. It's the same relationship right here. Where is it? Here it is, right? This relationship. I could also say in-person learning is worse than online, right? I can read it kind of backwards. That's why it's important to always have the same order. Online learning better, greater than in-person. That order of the hypotheses has to match. Anyway, if I think this is the relationship, online learning leads to better memory than in-person learning, then there's the theoretical, hypothetical, mathematical relationship between the two population means. My null is that they're not different. My alternative is that they're different in this particular way. Now notice what happens, right? If I were to do a subtraction according to this alternative hypothesis, I would get a difference between the population means that's greater than 0. There would be some difference, and it would be a positive number. Right? This is going to be a one-tailed test, and it's going to be in the upper tail, not because of the word better, but because of the difference that I would expect. If I think online is better, then I have a large number minus a smaller number, and I get something that is a positive number, something greater than 0. So we're in the upper tail for the rejection region, right? Because we're going to, in this case, if the alternative is true, we would expect positive difference between the two population means. Now let's consider the other one, right? Is online learning worse than in-person? Well, if online learning is worse than in-person learning, then this is the logical relationship. Online less than in-person. There's the relationship between the two means. And then in that case, what will happen is with my null, right? Again, the null has no difference, an equal sign. The alternative is online learning will be a lower mean than in-person learning, right? If online learning is worse, the mu OL is less than mu IP. Now look what happens when we turn this into subtraction. If we take a small number and subtract a larger number from it, we get an answer, a difference that is less than 0. So if this is the alternative hypothesis, this is a one-tailed in the lower tail. Right? We're in the lower tail because with this arrangement of the populations, online first, in-person second, and I do the subtraction, right, I would get something that is less than 0. Where'd it go? There it is, right? Something less than 0. So here's the summary, right? If we're doing a two-tailed test, you get the two-tailed rejection region, and it does not equal. An upper-tailed test is when we have a greater than in the alternative, right? And a lower-tailed test is a less than. But notice how these are set up, right? It is really dependent upon the kind of 0, the kind of answer you get if you were subtracting one from the other. In this, the upper-tailed test tells me that mu1, whatever that is expected to be larger than mu2, right? That is going to give me positive t values. When mu1 is expected to be less than mu2, I'm going to be looking for negative values of t. So here's the formula for the independent samples t-test, and the degrees of freedom for this test is one thing that's different. It's n plus n minus 2. Now, I couldn't quite get the subscripts to work there, but we take the n for the first sample plus the n for the second sample and subtract 2. Right, there's our degrees of freedom. There's the formula. I gave up trying to write it in PowerPoint, and that's a screenshot from the textbook, which is why it's a little bit fuzzy. But look what's going on with this formula, right? We've got right here the means from the samples, right? And here's the mean, here's the population means. Notice the order, 1 and then 2, 1 and then 2. You want to keep the order consistent whenever we do a subtraction. right? We compare the means, which mathematically means subtracting them. So really what we're doing is comparing the difference between the sample means to the expected difference between the population means. And we divide that by what we're going to call the standard error. But for now, just worry about this numerator. We look at the observed difference between the sample means, compare that, right? Compare that, that's the minus sign. Compare that to the expected difference between the population means. Now, according to the null hypothesis, this difference right here, according to the HO, right, mu1 minus mu2 is going to be 0. So this part effectively drops out, and we can use this as our formula for the independent samples T. We look at the difference between the sample means and divide it by the standard error. Now to find the standard error. The standard error is, there's the formula for the T again. The standard error is that thing right there. This bit, S subscript P squared. The subscript is actually the 2 should be a little bit over the S, but it is S squared. It's a variance, so S squared with a subscript of P, and that's called the pooled variance. We take the pooled variance divided by n for each sample, right? Here's one sample, here's the other sample. Add them together, take the square root, right? That's a formula for a standard error. Now to find the standard error, we need to find the pooled variance. So here's the formula for the pooled variance, and here's the symbol as it should appear in that other problem. Take the sums of squares for the first sample, add it to the sums of squares for the second, and divide it by n plus n minus 2. Now you probably recognize this from the previous slide as the degrees of freedom. Sums of squares, add them together, divide by degrees of freedom. That's a variance, right? Take this answer, right, and it goes in each of those spots. That's going to be the same number. There's only one pooled variance, and we use it twice in this formula for the standard error. It looks worse than it is. Trust me, it looks worse than it is. And we'll go through an example or two. Here's the example. Suppose my future self is interested in how learning during the COVID-19 shutdown has changed learning. So I can, I compare the grade averages for spring 2020 versus spring 19. I keep the spring semesters constant, right, for my sections of Psych 100. The data is below. Now, what is the data? I've got sample means for 2020. I've got sample means for 2019. X bar, X bar. I've got n's for each sample, and I've got sums of squares for each sample. I know this is an independent samples test because these are two separate groups of individuals. Part of the reason I know that is I have two different n's. And right, the subscripts, I'm just using the subscripts to keep my sample data clear. Does class type affect learning? Conduct the appropriate hypothesis test with alpha of 0.05. So that word effect, you see the word effect there, that tells me that this is going to be a two sample test. So according to the null hypothesis, right, the population mean for 2020 should be not different for the population mean from 2019, right? This is class style, doesn't affect learning, right? It assumes no difference between the two populations. So my null hypothesis is mu20 equals mu19. And, right, remember, if I subtract one from the other, that gives me 0, right? That gives me a real number that I can use to determine whether there is a difference or not. The alternative is, as we said, two-tailed, right? So it does not equal. If I were to subtract the two population means, I would expect something other than 0 if the situation of spring 2020 has somehow affected students' learning. So for this test, right, two-tailed, there's the hypotheses. Step 2 in hypothesis testing is the rejection region. So I'm going to keep the problem up there just so you can refer back to it. For a t-test, I know to find the rejection region, I need three things. I need the sign from the alternative, I need the level of significance, and I need the degrees of freedom. There's those three things for this test. Two-tailed, 0.05, and I've got 25 degrees of freedom. So what does that do? Well, there it is. Alpha 0.05, two-tailed, makes the rejection region look like that. I look up the appropriate critical value in the t-table, the 25 degrees of freedom, and we see negative 2.060 and positive 2.060. Those are my two critical values. So I'm going to reject the null hypothesis if we get a t obtained less than 2.060 or greater than positive 2.060. Now for the fun part, step 3, figuring out, figuring out the obtained value of t. So once again, here's the formulas, right? We're going to find the t. Now remember, mu1 minus mu2 effectively becomes 0. To find that, well, we need the standard error. There's the formula for the standard error. To find the standard error, we need to find the pooled variance. So the first thing we're going to do is calculate the pooled variance. I need the sums of squares for each sample in the numerator, and then the bottom is based upon n. Remember, that is the degrees of freedom. So there's the formula. 154 is the sums of squares for, I think that was online. 175 is the sums of squares for in person. There were 12 people in the online class, 15 people in person, 12 plus 15 minus 2. Do the math in the denominator as well as the numerator. Simplifies to 329 over 25, which gives me a pooled variance of 13.16. That's just the first step in finding the denominator. We got to take that pooled variance and find the standard error. The standard error, there's the formula for the standard error, right? The pooled variance twice, divided by each n, and then we add it together and take the square root. So it's going to look like that, right? There's only one pooled variance. We use it in both places. The n for the first sample is under the first one, and for the second is there. And you see the addition of parentheses. You see how this is going to work out. We simplify each one of those fractions and then add them together. So this becomes 1.1 plus 0.88. Add those two together, and we get 1.98. Take the square root of 1.98, and we get the standard error of 1.41. Almost there. 1.41 is the standard error. That's the denominator of the t-test. So, what's the t calculation going to be? Well, I need the two means, 83.5 and 79.6. Get the difference between them and compare that to the difference between the population means. According to the null hypothesis, right, the difference between the population means is 0. Right? What is that? Well, there's the difference between the sample means. But according to the null hypothesis, the difference between the population means is 0. Right? We couldn't do this if we didn't have the null hypothesis, because I would have no idea what that would be. But if we assume they're the same, they're not different, we get a 0. So that effectively drops out. So then what do we have? We have 3.9, the difference between the two sample means, divided by 1.14. Now here's where it's critical, right? The order of these means, 83.5, 79.6, has got to be the same order of the means as we had in the hypotheses. And we had 2020, sorry I said online learning, we had 2020 versus 2019. 2020 comes first. So the t obtained is 3.9 divided by 1.14 is 2.77. Step 4 is making a decision and stating the hypotheses. So there's the rejection region. That's what we found in step 2. I included the problem again. I think I might have lost track and said online and in person, but I forgot I changed it to 2020 versus 2019. So what do we have? We got T obtained is 2.77. 2.77 is in the upper rejection region, about where that green arrow would be. So the decision is reject the null hypothesis, and then the conclusion, we have evidence that spring 2020 students did significantly better than students in spring 2019. Notice this represents a possible type 1 error, right? I found evidence for something. It could be that that evidence is incorrect and I'm being misled. Independent samples tests are not that hard to pull off. It's a little bit tricky with the logic. Most important thing is being consistent. And in this problem, I had 2020 minus 2019 in every situation. 2020 always came first. As long as you keep that logical arrangement, then you have the right sign and you'll make the right decision. I want to do another example with you, and here it is here, but this slideshow's gone a bit long. This example I did in Stats Garage, so you can, I would recommend that you copy this down and try this example and then compare what you did versus the Stats Garage video, which is posted. The other thing I would suggest you do is go back and do that example 1. Make sure you can do it yourself. Go back to the first slide, do it, and then run through and see how it works. Take care.